Finally, we'll talk about real vortices. So, examples here are vortices in your bathtub as you drain it, or wingtips of airplanes, or a tornado is a classic example. So real vortices are neither the ideal vortex that we looked at last time or the solid body rotation vortex that we had before. They are typically a combination, and there's two standard ways of combining them. The first one is the Rankine vortex. So the Rankine vortex, omega z of r, is one where you have solid bodied rotation in one regime, so where gamma over pi sigma squared is constant for the regime for the radius smaller than some critical radius sigma, and it's 0 for the radius bigger than that. And the reason why you would do that is because in reality you won't have infinite vorticity at the origin as we had in the ideal vortex. So when you define your vorticity like this, you get solid body rotation for the small radius less than sigma. So that's a solid body rotation here, which is sensible near the origin, near the center of rotation for the vortex. And then at far distances you have an irrotational vortex, which is more reasonable because at far distances otherwise your velocity field becomes really large as it scales with the radius. So in this case, your angular velocity as a function of the radius would be r times gamma over 2 pi r squared for r less than sigma, and 1 over r times gamma over 2 pi for r greater than sigma. And so in this case you have, for the Rankine vortex, you have an abrupt transition between the two vortex types at r equals sigma. The second case that we will consider here is a Gaussian vortex, which has a gradual transition between the irrotational vortex and the solid body rotation. And this vortex is typically written as omega z as a function of r is gamma over pi sigma squared e to the minus r squared over sigma squared, and u of theta in this case is gamma over 2 pi r 1 minus e to the minus r squared over sigma squared. And so if we draw this graphically, your vorticity omega z for the Rankine vortex as a function of r. For the Rankine vortex, the vorticity takes one value up to sigma, and then it's 0. And this top value here is gamma over pi sigma squared, so that's Rankine. And the Gaussian one is just a smooth version of this. That's the Gaussian. And sorry, there was a typo up here. This is of course sigma squared, not r squared. Finally, if we look at the velocity fields for these two types of vortices we have for the Rankine, if you look up here, so u theta of r as a function of r. For the Rankine vortex, you have a linear increasing velocity up to your point r, sigma, and then a inversely decaying one down here. Whereas for the Gaussian, this down here is Rankine, and then the Gaussian one, u theta versus r, has this type of shape here. And that concludes our discussion of idealized simple flows.